Welcome to the latest webinar presented by Aerospace Tech Review, Flying into the Future with Safety Critical AI Capabilities. My name is Neil Walker, Conference and Marketing Director for Aerospace Tech Week and Aerospace Tech Review. Before we start, I'd like to point out the Q&A tab on the top right-hand side of your screen. You can ask questions there at any time during the webinar, and we'll try to answer as many as possible at the end of the session. If at any time your screen freezes, please press refresh and you should automatically rejoin us. So, artificial intelligence is an exciting technology being deployed across a range of industries to deliver more effective decision-making. Its adoption in aerospace and defence markets presents significant challenges in aligning with existing certification processes. AI is increasingly being used for handling and managing big amounts of data to find patterns, help avoid false positives and detect trends. However, there's also an element of safety and security behind allowing artificial intelligence making important decisions, and can these really be more intuitive than human intelligence? Today we'll be discussing the existing challenges, share industry best practices of how AI can safely harness in applications today, and predict how and when this technology will be incorporated into a more comprehensive set of mission-critical use cases. Today, we're joined by Lynx Software Technologies, Core AVI, and Intel as we explore how flying into the future with safety-critical AI capabilities. Ian Ferguson is the VP of Marketing at Lynx Software Technologies and responsible for all aspects of outward-facing presence, customer, partners, and analyst communities. Ian is also responsible for nurturing their partnership program to accelerate engagement in mission-critical systems. Neil Stroud is Vice President of Marketing and Business Development at Core AVI. He's spent over 25 years in the semiconductor industry in technical, commercial, sales, and strategy roles. For the past 15 years, Neil has been an industry leader in the functional safety domain, working closely with ecosystem, customer and partners across automotive, industrial, avionics and transportation segments. Debbie Aubrey is Technical Product Marketing Manager at Intel and has an accomplished systems engineering leader with more than 30 years of practical experience in developing and delivering products in a variety of markets, including scientific instruments, consumer electronics, digital broadcast systems, and tactical radio systems. So we're in for an interesting discussion, and I'll now hand you over to Ian Ferguson of Lynx to kick off with. Ian, the screen is yours.
Thanks, Neil. And I just wanted to add to Neil's warm welcome. We greatly appreciate you joining us to listen to this topic and hopefully interact, as Neil said, with questions, especially given today is Valentine's Day. So I don't know whether we're set up that AI is, a love topic, but in all seriousness, given everything else going on, we greatly appreciate you joining us today. We seem to have got to the end of the day. I think just to kick off, as Neil said, there are some challenges, right, around AI. We're in an industry where we rigorously define what our systems are going to do, and then we prove rigorously that they do what they say they do. And Neil is going to go in and talk about a little bit of the detail around neural nets, for example. And because they are more non-deterministic, how do we embrace that technology? And I guess one story for you, in the chip area, an EDA company in the last 2 years, a very large one, that builds the software tools that help people create SoCs, right? And these things have to run their circuits at a particular frequency. They ran and used AI to actually get a customer's chip running at a particular frequency, and nobody inside that EDA company could work out how the tool would do it. And that might be great if it's maybe a phone or an infotainment system where you can handle some on and off. But if we don't know exactly what the system's doing, how do we really know that on all corner cases our system's going to be robust if we think about the industry that we're all in? And as I say here, I think actually there is some good news. We're going to talk a little bit about best practices and where, for example, the European Agency for Aviation is going a little bit later in this presentation. If we just quickly think about certification levels, I think we're all familiar with this, where sort of as you go up this stack, the impact of system failure becomes more catastrophic. And you see on the right hand side the sorts of systems that line up to level A through level E. I think what you'll hear through this presentation is because of this sort of stack, what we're going to see is AI sort of starting at the bottom end of this area and sort of moving up towards a level A. But with that, I'll hand over to Neil, who can carry on from here and go into some more details on neural nets and some examples. Neil, if you there you are, you're on.
Yeah, can you hear me okay?
Yes, I can.
Okay, good. So AI is the use of computers or smart machines basically to simulate human intelligence. So carrying out tasks that humans would typically perform, such as language processing, speech recognition, image and vision processing. It makes use of machine learning and deep learning techniques. This AI system will consume, as Neil said at the top of the conversation, actually, huge amounts of data, and it analyzes it for patterns or looking at what can be happening and making predictions about the future states of those patterns. The key thing, obviously, is it can learn and reason and self-correct over time. So the theory is that the more it does it, the better it gets at doing what it's doing. There's no doubt we're on a journey with AI and come a long way in the time we've been working on this, from a purely reactive implementation to heading for a fully self-aware AI system sometime in the future. I mean, who knows when that's going to happen, but we're certainly on that journey. So then what are neural networks? So it's a key part of AI. They're essentially computing systems that are based on the architecture or the structure of an animal's brain. And they mimic the interconnections or the neurons that we have in our brains. It uses algorithms that have been trained to recognize certain patterns or data sets to solve complex problems, or look at images or listen to particular audio things to pick those out. And as we said, it's continually learning, continually improving at what it's doing. And I'll dig into a bit more detail of how neural networks work in the next slide. But we're seeing from a technology point of view that there's multiple ways to implement these neural networks. You can execute them on different compute elements such as CPUs, increasingly GPU implementations, and of course also NPUs as well, which are used quite frequently, but somewhat fragmented approach. More and more, we're seeing the use of heterogeneous systems where we bring together those various compute elements into a single system and try to right size them and implement those neural networks almost dynamically across those different compute elements, so you can right size for the given task at any one moment in time, so you're using the right compute element at the right time to solve the right problem. And that, of course, in itself adds a huge amount of complexity into the design itself. Okay, so how do neural networks work? Well, immediately you can see from the picture, you've got a number of interconnected nodes that simulate and mimic a brain's set of neurons. Any neural network is made up of 3 or more layers. So you can think of this as any kind of traditional computing system where you've got input, process, output. So starting from the left-hand side, you've got some data coming in, and that data can be from a sensor. So let's say it's coming from a camera. You've got a frame there of data that you want to process from a video, be it in a car or whatever. That comes into the input layer. The input layer then passes that data into what we call the hidden layers. So that can be made up of 1 or more layers, and you can see they're all interconnected, those nodes. And by applying weights and biases to these individual nodes based upon a training set or a model that's been developed offline, these neurons will then, or these nodes will then look at that data, and based on what it's seeing, each one will either trigger or not trigger, and then pass the data on to the next one, or pass that signal on to the next node or next neuron. And eventually that all gets processed and the result is passed to the output layer, and then you go do something with it. So that could be detecting an image that you were looking for in that specific frame. You either detected it or you didn't, and that data is then passed to the output, and you go do something with it based upon that data set, or that detection or non-detection. The challenge is, of course, is that you know what you've put in and you know what you get out, but you don't really know what's happening in the middle. And also how long that takes. So when we think about safety critical systems, of course, timeliness and determinism is critical. You need to know when you're going to get the result, because you're on a tight schedule to doing the next thing. So you need to know that a result's going to be available at a given moment in time. So using methods such as lockstepping, which is a tried and tested way of improving design assurance levels or safety integrity levels that we use in the CPU space, you can't do that with neural networks, because whilst you may still get to the same answer, the way you got there may be different, and also take a little bit of different time. So lockstepping is not really a way you can solve this. So of course that's forcing us all to look at different ways of solving the problem to achieve high integrity systems with AI. The other challenge, of course, is whilst this is very, very scalable, you can see how this approach can scale very nicely. Right sizing the neural network for the jobs in hand can be a challenge as well, especially when we think about avionics and getting the size and the weight and the power constraints sized correctly. So there's some of the challenges. We're all working as an industry to solve them, of course, and we're making great progress, but there's still a long way to go. So when we think about neural networks and safety, this kind of compounds the challenge that we have. And when we think about neural networks, we've kind of split them into two distinct areas. We think about the expression phase. So this is where we actually define the model, train the model of what it is we're trying to solve, the problem that we're trying to solve, or the image we're trying to detect, or whatever that may be. The execution piece is taking that trained model and actually executing it on real world hardware, for deployment. So going out into the big wide world, into the vehicle, or into the aircraft, or whatever that is. And as we just said, execution has to be deterministic. Safety systems must be deterministic. And for the most part, that's achievable. But for AI, that can create some issues. And historically, we know that there's not been an inference engine that can do deterministic execution, and that's been a real blocking factor to enable certification, regardless of the certification standard you're looking at. This is an industry problem. So whilst this of course applies to aviation, it applies to every other cert standard out there as well, whether you're doing robotics or transportation, industrial automation, or the vehicle as well. So there's of course a lot of focus across the safety industry to solve this challenge. So thinking about real life AI examples, well, it's all around us. We're all interacting with AI capable machines every day of our life. With whether it's Amazon Alexa, of course we all use that. But it's used in industrial automation for smart factories to make sure that we're building things in the most efficient way and changing on the fly. There's a lot of AI that goes into that. Of course, from a stock market perspective, if you can execute that transaction, a millisecond faster than somebody else, that equates to millions and millions of dollars in profit over time. And of course, you can spot trends and react to those as well to drive those profits up. But increasingly, of course, we're seeing AI being used in safety critical applications. Of course, it has uses in those kinds of scenarios. I guess the most prominent one is around self-driving vehicles. It's receiving a lot of, I would say, positive and negative press right now. I think generally the industry realizes that it's a hard problem to solve. And whilst we're making good progress, I think there's still a long way to go. And of course, It's not just about solving the technology around AI. There's the ethical piece to it as well, and the infrastructure piece and the legislation piece, which again applies equally to different market segments as well. So we've got a lot of work to do here. We've got a lot of experience we can draw upon as well, and that's really helping us as we traverse this journey. So the key thing we wanted to mention is that, of course, AI is happening in avionics today. It's happening right now. We've got examples of where it's being deployed today, and we're also working actively with a lot of our customer base to develop and deploy AI systems with a safety critical element to them. Of course, it's starting with the lower design assurance level implementations, going back to Ian's table at the beginning of the presentation. We've also seen some significant resetting of expectations. I think if we use the reference point of automotive and autonomous vehicles, there was a lot of hype around that going back a few years, and we predicted that we would have fully autonomous vehicles, mass deployment, by now. It obviously hasn't happened, and especially recently, there seems to be a little bit of a sink into the valley of disillusionment. So we've got a long way to go. I think people now are understanding that it's a big investment. It's not as simple as we first thought, and there are issues to be solved that we have to keep working on. Of course, as we look at autonomous vehicles as a reference point, which we are seeing customers in the avionics space doing so, one could argue that solving the problem in avionics is perhaps a little bit easier because you haven't got as many things to run into. The scenarios and the operating domains are somewhat simpler because think of a busy high street. There's a lot of things going on that you have to process. That's not necessarily true for a flying thing. Clearly, as well, replacing the human pilot is a long way off. We hear about things like loyal wingman, where it's augmenting a human pilot, but there's still a long way to go before we fully replace the human pilot and we've got fully autonomous flying machines. Controversially, of course, going back to the deterministic statement as well, one can argue that the human in the loop is not deterministic either. So we kind of got to overcome that dichotomy. But what's clear is the industry generally is embracing artificial intelligence today, and that's going to be an ongoing trend. And we've got to right size the systems. We've got to create systems that are going to manage the ambiguity that the world delivers to us and deal with that ambiguity in the most appropriate and deterministic way. So another exciting trend I wanted to mention to you. So more from a software point of view. So recently, Core AVI have been working very, very closely with a company called CoPlay, who were recently acquired by Intel, to develop and establish a working group within the Kronos organization to deliver a safety critical implementation of SQL. Now, SQL, as you know, it kind of bridges the gap between low-level APIs and high-level programming environments such as C++. The key thing here is that it'll allow us as an industry to go deploy neural networks and AI and machine learning in a deterministic way on top of the compute elements. Typically GPU is a good example. Of course, also allows migration from other language out there like CUDA as well, with a clear path to safety certification. We're still in the early days of this. The working group within Kronos should be established within the next few weeks, but this is an exciting step forward, and stay tuned for more news on this. So I just wanted to dig into a few examples of where we're seeing AI being used in avionics today and in the near future. So one area is around air-to-air refueling. So typically this is a task that would be very human-driven, but Airbus have deployed the system now, which is AI capable, and it's fully automated. So this obviously allows this to happen more safely, more quickly, and in a more automated manner. And then referring back to Ian's DAL table earlier on, this is probably a DAL C, DAL D kind of application, so lower down that safety integrity stack, but nevertheless a good proof point of where this is being used. Of course, we hear more and more about last mile delivery of parcels and food, etc., to our homes. So the drone deliveries are going to become an increasing part of our life as well. And of course, if it's automated, it's also got to be certified because it's flying in public airspace. So this pushes up the levels of integrity, safety, integrity, and design assurance that it's going to have to be certified to. Of course, we've got the other problem as well of congested airspace, but that's out of scope for this discussion. But this, nevertheless, is going to become an increasing use case for our world going forward. And we're seeing some of these being deployed as proof of concepts today, of course. And then to mention the X-59 low boom project. So this is an experimental aircraft, but the key thing here is it's a windowless cockpit. So everything that the pilots use to interact with the outside world is projecting onto a screen. So this is a great example of combining both graphics and AI, augmented reality, into one system and one use case for the pilots to use. Of course, this will be a design assurance level A application, because if the system goes down, you can't look out the window and see what's going on in the real world. So very exciting. This is flying today as an experimental aircraft, and Core AVI has the software in that windowless cockpit. So with that, I'm going to hand it back to Ian.
Oh, sometimes getting back off mute on this tool is challenging. Thanks, Neil. I'm just observing that we're 20 minutes in and we've managed to avoid the use of the phrase chat GPT. So we'll see whether we can manage that for the next 40 minutes. Just wanted to sort of dig in a little bit into what the software foundation underneath these platforms is going to be looking like, based on our discussions that we're having with some customers, and I think, just like Neil said, given at least near term some of the ambiguities around determinism for AI. One of the main areas is how you sandbox these functions. You're going to have to look at how you allocate time for a particular function, so that it doesn't sort of, you're not sitting there waiting for an answer and something else can't get access to the system resources they're going to want. The second item is, these systems are going to need to be continually evolving, getting updates to the models, LLMs, large language models like ChatGPT or others. And so the good news is your system have to become connected. The challenging thing is that your systems become connected, right? And while we tend to think about all the goodness that connection can provide, you've obviously got to think about people that are going to use that connection as a weakness point to go off and try and insert malware. And then the third element I'm going to talk about is certification strategy, and share a little bit more, like I said earlier, about certainly where the European agency is going in terms of its recommendations for AI. So just to dig in, and we see customers increasingly looking at cloud backends for these systems, whether those are private cloud or public cloud. We've seen both. I think the first thing is you're going to see some sort of framework where you sandbox and isolate these functions. So you're going to need to move to a hypervisor architecture. You're going to have a mix. We've seen some people building, bare metal code, very tight. It's their own code. They write their own algorithms. So from that point of view, it's compelling. I think the shift is going to go towards, more of an open architecture, embracing, all of the learning that's going on around these models, like Neil described. So I think we'll see a shift towards real-time operating systems, or more likely, Linux running some of these subsystems for AI. But the role of the rest of the system architecture is how do you partition that up, isolate the apps from each other, and again control from a timing point of view how much time that particular AI task has. You can't just be sitting there with the system waiting for an answer before it moves on. And then, I think the sort of AI you cannot see is what I'm sort of framing with the cybersecurity. And, I think there's been a lot of focus about building a bigger and bigger impenetrable wall for security. If you look around, there are a lot of people that have their system compromised, and they don't actually realize it for months. And that's a problem, because it's going to take somebody a while to go off and find the valuable assets and how to sort of compromise systems. So I think the shift, one of the great areas of opportunity for AI is to actually start to identify when systems have been breached, and we think of it in three phases. Firstly, setting up, defining normal. So what is the normal behavior for the system? And, I think this is a responsibility for everywhere in the stack. I think down at the hypervisor level, you're seeing what loading looks like on CPUs, what memory accesses look like, what network interface and patterns look like. So you define normal. And from there, you start to be able to identify abnormal. And that's, you see here, sort of things like, rootkit detection, strange API requests and things like that. And then thirdly, you have to handle abnormal. And there's obviously different ways, bringing the system back to a known working state, shutting down that VM, and removing yourself off the IP network, whatever those things might be. Those are the three phases that we're increasingly seeing our customers take. And this is at the hypervisor level, but probably the decisions on what you're going to do with how you handle those abnormal behaviors will be sort of rolled up into an application of some description in a virtual machine, a secure virtual machine, that then can say, well, based on this, I'm going to take this action, or this action. And I mentioned a couple of times, Isa, I think there is some very thoughtful work in the public domain that I would recommend going and looking at. Their first release came out about just over a year ago, at the end of 21. And they've sort of taken what we've been talking about with DAL assurance levels and sort of flipped it a little bit, if you look at the one on the right-hand side. So they basically define systems from a level 1A down to a level 3B. And, down this chart is an increasing level of, catastrophic. If you make your decision incorrectly, the bottom of the list, there's more catastrophic consequences than at the top. So, initially, and like Neil was saying, with a number of the near-term examples, we're really sort of offloading items from the human pilot, and helping, the AI is making better decisions as a helping function, as opposed to sort of steering the whole plane itself. And as you walk down here, you get to, increasing levels of autonomy. So really good document. They brought out a very detailed paper in the public domain that talks about how AI can be embraced for these level 1 machine learning applications that you see up here around human augmentation and assistance. They're working on level 2, and we should be seeing that during this year. And the other thing I wanted to mention was, there's been sort of quite a bit a few years ago was about explainable AI, and the idea there was, right, well, we're going to absolutely know everything about exactly how a calculation is made. We're going to know accuracy. We're going to, all of these pieces, and I just don't see that. I think, from our conversations in the industry, we're moving more to a theme around certifiable AI, and just given the fact that outputs are unexplainable, confidential, I think we're shifting to a world where we're going to have to demonstrate that the system is fit for purpose and has no unintended function, and that's going to come down to looking at the algorithms that are being used, but also to that last point, the fact that you've bounded that AI functionality in a way where you've defined how that function is going to interact with the rest of the systems, not just in terms of data paths, but also in terms of time determinism and things like that. So I think this is the path, and I think that as Neil said, I think the equivalent of level 5 autonomous vehicles, which has been really a struggle. We're absolutely seeing that there is a shift, and we will see fully autonomous a craft in the sky in the not too distant future. This is the outline from ESA, as I mentioned, the European Union of Aviation Safety. This is their timeline of where they're looking to bring out some of their deliverables. You see here that they're a little bit behind on where they said they would be with the level 2 AI ML, but we do expect that to come through. But we will start to see, if you look down at the bottom here, they're believing that we'll see first approvals of AI and ML in the 2025 timeframe. And I think if you see some of the other announcements from companies in the US like Joby, Archer, I think that sort of lines up roughly with what we're going to be seeing in the US too. So a lot of work to do, as Neil said, and we've got to make sure we don't, as an industry, sort of end up in the same place as some of the missetting and missteps of the level 5 vehicles. But I feel very good about the path that we are on. With that, let me hand over to Debbie.
Good morning. So my name is Debbie Aubrey. I'm the Technical Product Marketing Manager at Intel for our Federal and Aerospace segment. And we're going to talk just a little bit today about how Intel's technologies are enabling safety critical avionics, and particularly Intel's capabilities around AI related to the coming unmanned aerial systems revolution as we see it, as well as our core processing capabilities to manage combining workloads, combining applications into one piece of silicon rather than 3 or 4. I just wanted to start for the folks in the audience with a list of some of the relevant avionics standards that we're referring to. Of course, I think most people are familiar with the top 2, the DO-178C, the DO-254. Intel in particular is mostly involved at the DO-254. So, as we're delivering silicon, we're trying to provide you with evidence around how our silicon behaves. And the other 2 that are particularly relevant to Intel are the AMC 20-152A, which prescribes development assurance guidelines for silicon, as well as AMC 20-193, which talks about determinism with multi-core processors. And then moving forward on the AI ML standards, I think Ian gave a very nice sort of overview with regard to where EASA is. The FAA is a little bit behind EASA in publishing some of these standards. However, we do have some existing, and these really are related to detect and avoid systems, air-to-air radar, as well as the electro-optical infrared sensor systems relative to that urban urban air mobility segment as it's coming forward. So this is just for your reference. Now, what Intel is doing to facilitate our customers in developing these packages, their certification packages, is we're providing a license to the Intel Airworthiness Evidence Package. And that is a collection of documents under NDA where it's documents we don't normally offer to customers. The other thing about the licensing this package is that normally a customer who has access to Intel documentation is allowed to review that data and incorporate it internally. However, you're not allowed to incorporate that data into documentation that is going to be shared with other customers. And of course, when you're developing your own certification package that you need to develop to regulations, the regulatory agencies, you need to be able to incorporate Intel data into your packages and deliver it to those certification agencies. And that is what one of the purposes of the license, to allow you to share that data with the certification agencies. Our AEP helps address the design assurance considerations related to the AMC 20-152A. And then, of course, there's our silicon, where we have integrated a number of capabilities, such as time-coordinated computing, as well as some artificial intelligence acceleration primitives that allow you to, leverage that silicon in order to develop your applications. So when you look across an aircraft, of course, there's a number of different systems, and each of them is going to be classified at a different design assurance level. So some systems will absolutely require DAL-A certification, while others are only going to require perhaps DAL-D and perhaps even DAL-E classification. And what Intel offers is a full range of products that will meet the performance requirements, as well as your size, weight, and power requirements. So you have a variety of options to select across Intel's product line. Our airworthiness evidence package is meant to accelerate your time to market, because we provide the evidence which prevents you from having to characterize the silicon yourself. So that can take a lot of time and money. We provide a lot of reliability data. So that's around our failure in time, so what our fit rates are, as well as things around our as well as things around our real-time performance and functional safety. So we provide quite a lot of data there. Probably one of the most relevant aspects to Intel Silicon is our integrated Iris Xe graphics architecture. This includes a deep learning boost AI engine, and when you pair this with our high performance core, this allows you to have the ability to integrate and power your AI workloads within fewer core processors in your system. The integrated Intel Deep Learning Boost includes vector neural network instructions, and these deliver significant performance improvement by combining instructions into multiple instructions into one that allows you to maximize the use of the computer resources. It allows you to have better use of our cache, as well as avoiding potential bottlenecks. And all of this is working towards providing a certifiable AI roadmap. Looking back at the AMC 20-152A standard for design assurance, the Intel is, of course, providing COTS devices, and the AMC 20-152 design guidelines give requirements around what kind of data is required for those COTS devices. And Our airworthiness evidence package includes data around the product lifecycle with some descriptions and milestones so that you have confidence in Intel's design approach to developing these highly integrated devices. We have NDA with the customer, and once we have that NDA, it gives you access to our resource and documentation center. And in there, there's a lot of data around specifications and errata, and of course, once you have a license in place, you can integrate those details into your certification packages. Then we also have a number of other things, that are standard with Intel, where we provide you product change notifications and end-of-life notifications so that you have an understanding of where the sightings are happening and when the products are reaching end of life. From a determinism perspective and a flight safety perspective, we provide a number of documents as a part of the airworthiness evidence package, one of which is the AMC 20-193 guide. This was formerly known as CAST 32A. This guide provides some tuning recommendations for real-time applications. It addresses things in the hardware, in the BIOS, as well as the graphics, integrated graphics processor in the chip. We provide a dependent failure analysis, and this is performed to identify single events or single causes that could result in the failure of 2 or more components, resulting in cascading failures which could violate safety requirements. We provide the freedom of from interference analysis for both our hardware as well as the microcode. And this is performed to determine whether faults in the components with less critical DAO levels could influence the components that are more critical from a DAO level perspective. And our failure mode effects and diagnostic analysis contains the results of our analysis to anticipate failures during the design stage. We identify the possible failures and then provide what are the mitigation measures in place in order to achieve your required safety integrity level. From a determinism perspective, the Intel has incorporates time coordinated computing capabilities into the chip. So that's Intel TCC. And this allows time sync. It facilitates time synchronization between the components within the chip as well as timeliness for delivery of data. It's all incorporated under the umbrella of the Intel Resource Director technology, and there are a number of different features, including cache monitoring technology, our cache allocation technology, memory bandwidth monitoring, as well as allocation. And these different functions are focused on use cases where missing a deadline is a system failure. So our real-time offerings support new solutions, and they deliver both high compute and real-time performance. And we do that by helping our customers understand how to prioritize their real-time workloads, access to cache and memory and networking, trying to minimize disruption and interference between the workloads or between the applications that are hosted on that CPU. And we also optimize performance for both real-time and non-real-time workloads. So really with the goal of ensuring availability in both native and as well as virtualized environments. One of the other things that we do is we provide very specific avionics SKUs. The one that we have currently and having the most interest in is our Core i7 1186 GRE. And within the SKU, we've specifically disabled our thermal throttling logic in order to ensure that the chip is not making any decisions regarding the heat of the chip. So when the chip gets too hot, we don't want it to automatically throttle when it's processing a safety critical workload. So the this processor, the 11th gen Intel Core processor family, has the integrated graphics processing unit with the AI acceleration primitives included. We are, part of this. The goal of this chip is to start powering those aerospace applications. So things like the integrated flight decks and visual AI. Most of the work being done right now for the unmanned aerial systems is focused on a pilot-assisted system. And what you see in the legacy aircraft market as well is that we're starting to remove, try to take one of the co-pilots, take the co-pilot out of the cockpit and with only one pilot, and that's driven by a number of different macroeconomic sort of issues. So one of which, of course, is the availability of pilots, and so that goal of reducing in a legacy aircraft to one pilot, as well as looking forward to piloted unmanned aerial systems as part of phase 1, is leading us to have the more integrated capability of sensor processing. And the Tiger Lake processing family provides that integrated core with the AI to help offload and combine your applications into fewer pieces of silicon inside your solution. And we have included in the presentation some pointers to online resources, and then you have my contact information if you have any further questions. And I think with that we can move forward.
Thanks, Debbie.
Yes.
Yeah, so I was just going to move to some Q&A. I had some interesting questions come in. Obviously, feel free to fire in as many questions as you like. Neil, one that came in that maybe you want to take a first pass at was what would a typical execution AI deterministic software stack look like?
I'm going to give you the biased answer. I think from a core AVI perspective, we obviously use Vulkan SC, Vulkan Safety Critical, as that kind of hardware abstraction layer. So we'd use that as the baseline interface to the underlying hardware. Of course, we support Tiger Lake with that today as well. And then on top of that, there are a number of different approaches. Obviously, we've got products that focus on compute generally, so executing support of BLAS and FFT types functions. And of course, the Sickle SC, Sickle Safety Critical that I mentioned earlier on, is an exciting addition to that as well. And incidentally, the Sickle SC emerging standard shows that being put on top of Vulkan SC as well. So it enables developers to really scale across multiple platforms and using that Vulkan Sickle SC layer as almost as a hardware abstraction, and getting good performance out of the underlying platform whilst future proofing as well. We're actually joined by Ken Wenger on the call, who's the Senior Director of Research and Innovation at Core AVI. So perhaps you can add a couple of words to that as well, Ken.
Thanks, Neil. I think you addressed it pretty well. They have in terms of having a fully safety critical stack for AI, what you want to have is you want to be able to have a set of products or libraries that enable you to access the device, the acceleration device, at different levels of abstraction, and hopefully you have those libraries implemented on a safety critical API for each of those levels. So, for example, on the lowest level, you have the device driver. And for that, we have something like Vulkan SC, which lets you give access compute capabilities of an accelerator on a much lower level. So this is like, if you're familiar with OpenCL, it's a bit lower level than that, but it's that's kind of what you get from a Vulkan SC compute pipeline. It's direct access at a very granular access point to the hardware. And then as you you become abstracted from the hardware and you build up a stack, you want to have things like, as Neil mentioned, math libraries for BLAS, FFT. You want to have a neural network inference engine, for example. And then on top of that, you also want to have the ability to write very high-level general purpose compute code on a high-level language, so something like C++, for example. And then you want to be able to have that somehow magically accelerated behind the scenes. And again, using safety-critical APIs underneath. And one way to do that is with SQL Safety Critical, which is what Neil mentioned that we are we're working on. So the idea of a full safety-critical stack is based on products that build on each other and all use safety-critical APIs. Hopefully that answered the question.
Cool. I'm sure people can use the chat if it didn't. I guess, Debbie, one for you was a question about Intel's AI products and whether you've been thinking about cosmic radiation and have plans and work with customers to address potential susceptibility there.
Yes, thank you for that question. So as a part of the airworthiness evidence package, we include 2 documents related to single event effects. We include the soft error rate report as well as a single event upset analysis, and these are both included in that package.
Okay, and maybe a follow-on, just because you're on a roll, Debbie. Somebody was asking, is there any risk introduced by disabling the thermal throttling function?
Yes, in fact, that's one of the issues around that chip. It's not really an issue, it's designed that way, because what our customers have asked us for is they do not want the chip to do anything on its own, especially in a DAL-A certification certified system. So if the chip overheats, then they would much rather have the chip melt than to affect the criticality, the safety of the system. And so when integrating that chip into your system, the customer is going to be responsible for mitigating the thermal effects of running that chip. So you still will receive all of the interrupts letting you know that chip is starting to run hot so that you can do some active mitigation outside the chip. But the most important thing is that we're not doing anything without you having an understanding of what's going on. So the chip is not going to do anything on its own to affect the performance of the system.
All right. That was very thorough and very open. Appreciate that, Debbie. I guess another one for you, Neil. Someone was asking about when, you got your crystal ball. When do you think safety critical SQL will be available? And you are just, no pressure, you're being recorded, so your result is going to stick around in the ether. So
that's okay. I got my crystal ball here, so I'll dust it off. Well, so I'm going to use Vulkan SC as kind of a reference point, and the kind of the time period that took, and that was probably from inception to ratification somewhere between 2.5, 3 years, something of that order. So let's assume we get the SQL SC working group up and running in the next few weeks. Let's say ratification a couple of years or so from that date. Of course, we and others will begin to develop an implementation ahead of ratification when we think there's enough maturity in the emerging standards. So that's always a little bit of a gamble, but of course there's a desire to get your hands on it as soon as you can, with the risk that goes with doing that pre-ratification as well. So yeah, exciting time, and I have to say there's a good momentum behind it from not just us and CodePlay, but of course industry players as well across various market segments. So there's clear desire there.
Okay. I was just looking through the other questions.
Yeah, I had a
Neil,
question. I was going to say I had a question for Ken. There's a good question earlier on from one of the attendees. I think I made a statement in my section of the presentation around the execution must be deterministic. And is that talking about computation in bounded time, or the results of the computation, or both? And I was going to throw that one at Ken, seeing as he eats, sleeps, and breathes this stuff.
Thanks, Neil. Sure. So I think that's a very good question. There are three separate parts to that. So the execution of a model certainly has to be deterministic. So I think that is the least controversial part of the question. And that's because you typically have a device that's being shared by many different applications running on that same device. So the very least you have to do is guarantee determinism of execution. But then the expression of the model, so the output of the model, there is two parts of that. There is first determinism in terms of if you give it an input, it gives you an output. If you give it the same input, again, is it going to give you the same output? I think on most models, and it depends on the type of model we're talking about, there are models that are inherently non-deterministic. But models which are mathematically deterministic, I think you can ensure that the answer is deterministic, right? So you provide an input, it'll give you an answer, and you can provide the same input many times, and it should give you the same answer. So that should be deterministic, as long as the model itself is mathematically deterministic. Now, there's another part which is a little bit more. I would say it's still in the research phase, which is how do you know that the answer is correct given the input, right? And whether that part can be deterministically proven eventually or not, that's what it's currently still being defined. So, for example, do we need to prove the output being correct given certain input, or can it be at least probabilistically defined? So, given a certain range of inputs, you can expect these types of answers with this margin of error. So all of these things are still being defined, but I think at least two parts of it can be deterministic. The execution certainly has to, and the fact that an input should provide the same output multiple times can also be expected. Again, hopefully that answers the question.
Excellent. Debbie, one for you. You obviously everyone's very excited about some of the packaging of the technology you were talking about earlier. You'd mentioned cache monitoring tooling and interference analysis. The question was, do you provide those services for the SoCs, including the GPU side of your product?
So yes, the time-coordinated computing capabilities are actually integrated into the chip, and the GPU is included in that. Some of the other, around the time-coordinated computing, we can allow you to actually allocate cache and bandwidth to the GPU that would be separate from the CPU. So we allow that type of configuration. In addition to that AMC 20-193 IA guide, which is very specifically focused on, the guidelines relative to what was formerly CAS 32A, right. We also provide a real-time tuning guide, which provides much more detail around, what are the time-coordinated capabilities and how do you configure them in far more detail. So the AMC 20-193 guide is mostly focused on interference and how do you mitigate the interference in the system and where will you see the interference within the CPU, whereas the real-time tuning guide is a bit more generic in terms of helping you understand what those capabilities are.
All right. Neil Walker, I was just looking at where are we time-wise? So I think we're probably, I don't know whether if we can answer any more questions, we're going to be out of time. You're our time cop.
Yeah, no problem at all. I mean, if you believe you got through the questions, we're good to wrap up. So thank you very much, Ian, and thanks Neil and Debbie also. It's very interesting and insightful discussion and presentations. We enjoyed it. I hope you all did as well. So thank you very much all, and just to remind you that the Aerospace Tech Week Europe exhibition and conference will take place on the 29th and 30th of March in Munich, Germany. You can register now online. The conference early bird rate is 28th of February, so book now and save on your conference delegate pass. You can also register for a free expo pass at www.aerospace-techweek.com/Europe. Aerospace Tech Week Americas is also back in Atlanta on the 14th and 15th of November 2023. The call for papers will be open in early April, so keep a lookout and submit your abstract at www.aerospace-techweek.com/Americas. You can also keep a lookout for the next webinar from Aerospace Tech Review at aerospace-techreview.com. But for now, thanks again to the Aerospace Media team for today's speakers from Lynx, Core Avi and Intel for today's webinar. Most importantly, thanks all to you for joining us today's webinar, and we look forward to seeing you next time. Thank you and have a good day.